This video is on hypothesis testing. If you've taken a statistics class before, you probably know that there are different types of hypothesis tests. This video is just meant to introduce you to the overall topic of hypothesis testing. I won't get into the details of the different types of hypothesis tests until later videos. Basically, hypothesis testing is used to reach conclusions during research studies. It's the use of calculations to reach a conclusion at the end of a study. Since this video is meant to introduce you to hypothesis testing, I won't cover the calculations that are used during research studies. Instead, I will talk about how hypothesis testing can be used to reach conclusions during daily life situations. I'm hoping that this will make it easier for me to introduce the vocabulary and calculations that are used during hypothesis testing. And I'm hoping that it will also make it easier to understand the calculations and vocabulary once we start to talk about research studies later on. In this video, I won't start with calculations. I always start with talking about the big picture first, and then I slowly move into calculations later. The purpose of a hypothesis test is to collect evidence to decide between two competing possibilities, called a null hypothesis and an alternative hypothesis. I'll start by giving you a basic or common sense definition of these two terms. The null hypothesis is the possibility of the absence of something. The alternative hypothesis is the opposite of the null hypothesis. It's the possibility of the presence or the existence of something. Now let's look at some different situations and try to find out what the null hypothesis and alternative hypothesis would be. Imagine that someone wants to know if they have a cold. In this situation, the null hypothesis would be that the person does not have a cold. The null hypothesis would be the possibility of the absence of the cold. Remember, the null hypothesis is the possibility of the absence of something. The alternative hypothesis is the opposite possibility. The alternative hypothesis is the possibility that the person does have a cold. So it's the possibility of the existence of the cold. It's the possibility that the cold does exist. So this is situation one. What's another situation? Maybe a person wants to know if there's a mouse living inside the walls of their home. In this situation, the null hypothesis would be the possibility that there is no mouse living in the walls of their home, And the alternative hypothesis would be the possibility that there is a mouse living inside the walls of their home. So the null hypothesis is the possibility of the absence of the mouse. It's the possibility of no mouse. The alternative hypothesis is the opposite possibility. It's the possibility that the mouse, it's the possibility that there is a mouse inside the walls of the home. So it's the remember that the alternative hypothesis is the possibility of the presence or the existence of something. So in this situation, the alternative hypothesis is a possibility that the mouse is there. So the null hypothesis says no mouse. The alternative hypothesis says there is a mouse, because the null hypothesis is the possibility of the absence of something, and the alternative hypothesis is a possibility of the presence or the existence of something. Let's look at one more situation. What if a person wants to know if his or her computer has a virus? The null hypothesis would say that there's no virus, and the alternative hypothesis would say that there is a virus. Because the null hypothesis is the possibility of the absence of something, and the alternative hypothesis is the possibility that either something is present or something exists.
In each of these situations, the person would like to know if the null hypothesis or the alternative hypothesis is true. What types of evidence could the person gather in each of these situations to decide whether the null or the alternative is true? In situation 1, in which the person wants to know if he or she has a cold, the person could count the number of times that he or she sneezes during the day. If the person sneezes only a small number of times during the day, like 1 or 2 times, then the person won't be convinced that he or she has a cold, because a person could easily sneeze 1 or 2 times just by chance. So if the person only sneezes a small number of times, the person will assume that the null hypothesis is true and that the person doesn't have a cold. But if the person sneezes a large number of times, like 10 times, then the person will be convinced that he or she has a cold, because a person wouldn't be likely to sneeze 10 times just by chance. So if the person sneezes if the person sneezes a large number of times, then the person will be convinced that the null hypothesis is wrong and that the alternative hypothesis is true. In other words, if the person sneezes a large number of times, the person will be convinced that he or she does have a cold. What about in situation 2? In this situation, the person wants to know if there's a mouse living inside the walls of the home that they live in. In this situation, maybe the person could count the number of noises that they hear during the day. Maybe the person could count the number of noises they hear from inside the walls of the house. And this works the same way as in situation one. If the person only hears a small number of noises, like one or two noises during the day, then the person won't be convinced that there's a mouse living inside the walls of the home, because those one or two noises could easily happen just by chance. They could just be random noises. So if the person only hears a small number of noises, the person will assume that the null hypothesis is true, and that there's no mouse living inside the walls of the home. But if the person hears a large number of noises, like 10 noises during the day, then the person will probably be convinced that there is a mouse living inside the walls of the home, because it isn't likely that the person would hear 10 noises during the day just by chance. So if the person hears a large number of noises, the person will be convinced that the null hypothesis is wrong, and that the alternative hypothesis is true. In other words, the person will be convinced that there is a mouse living inside the walls of the home. What about in situation 3, in which the person wants to know if the computer has a virus? In this situation, the person could count the number of times that his or her computer freezes during the day. And just like before, just like in these other examples, if the computer only freezes a small number of times, then that's not really good enough evidence to conclude that the computer has a virus, because the computer could freeze one or two times easily, even without a virus, but it's unlikely that the computer would freeze a large number of times just by chance. So, if the computer freezes one or two times, then the person will assume that the null hypothesis is true and that the computer doesn't have a virus. But if the computer freezes a large number of times, then the person will be convinced that the computer has a virus. In other words, if the computer freezes a small number of times, the person will assume that the null hypothesis is true. But if the computer freezes a large number of times, the person will be convinced that the null hypothesis is wrong and that the alternative is true.
In each of these situations, there's two possible decisions that can be made. If enough evidence has been collected, the person will decide that the null hypothesis appears to be wrong and that the alternative hypothesis appears to be true. That decision is called rejecting the null hypothesis. If not enough evidence has been collected, the person will continue to assume that the null hypothesis is true. That decision also has a name. It's called failing to reject the null hypothesis. What that pretty much means is that the null hypothesis has not been rejected. The null hypothesis continues to get the benefit of the doubt. So, if I sneeze one time during the day and I'm not convinced that I have a cold, and I just continue to assume that I don't have a cold, and I continue to assume that the null hypothesis is true, that's called failing to reject the null hypothesis. It's pretty much just a non-rejection of the null hypothesis. If I sneeze 10 times and I decide that the null hypothesis is wrong and that I do have a cold, that's rejecting the null hypothesis, because I've rejected the possibility that I don't have a cold, and I've concluded that I appear to have a cold. So you either reject the null hypothesis and conclude that the alternative appears to be true, or you don't reject the null hypothesis and you just continue to assume that the null is true. Um, if I only hear one noise during the day and I assume it's just a random noise and I'm not convinced that there's a mouse living inside the walls of my house, then I've failed to reject the null hypothesis. In other words, I haven't rejected the null hypothesis. I'm continuing to assume that the null is true. That's what failing to reject the null hypothesis means. If I hear 10 noises during the day and I'm convinced that there is a mouse, and I conclude that there is a mouse living inside the walls of my home, then I've rejected the null hypothesis because I've rejected this possibility that there is no mouse, and I've decided that I think that there is a mouse. Over here in situation 3, if my computer only freezes 1 or 2 times, and then I assume it's just something that's happening randomly, and that my computer doesn't have a virus, then I'm just sticking with the null hypothesis. I'm not rejecting it, and that decision is called failing to reject the null hypothesis. Failing to reject the null hypothesis means you give the null hypothesis the benefit of the doubt because you haven't collected enough evidence against it. If my computer freezes 10 times and I conclude that my computer does have a virus, then I've rejected the null hypothesis. I've rejected the possibility that my computer is fine, and I've decided that my computer does have a virus. I've decided that I think the alternative is true. So in each situation, you either fail to reject the null hypothesis or you reject the null hypothesis, depending on how much evidence you've collected, depending on how strong the evidence is. And let's try to visualize the evidence on a number line in each of these situations. So before I do this, I wanted to say that the overall logic of hypothesis testing is that if an outcome happens that would be unlikely to happen if the null hypothesis was true, then the null hypothesis is rejected. So if I sneeze 10 times during the day, then I reject the null hypothesis. And the reason why is because even though it would be possible for me to sneeze 10 times during the day when the null is true, it's not likely to happen. On a day when I'm not sick and the null hypothesis is true, I'm unlikely to sneeze 10 times just by chance. So sneezing 10 times is an outcome that would be unlikely to happen if the null was true. That's why if that outcome does happen and I do sneeze 10 times, then I reject the null hypothesis. So I'll say that this is the overall logic of hypothesis testing. Reject the null hypothesis. If an outcome happens, it would be unlikely to happen if the null hypothesis was true. Or you could say, if an outcome happens that would be unlikely to happen in the situation of the null hypothesis being true. Otherwise, continue to assume that the null hypothesis is true. So in situation 2, if I hear um, 8 or 10 noises during the day, in other words, if I just hear a large number of noises during the day coming from the walls of my house, then I know that if the null hypothesis was true and there was no mouse living inside the walls of my home, then in that situation, it wouldn't be likely that I would hear 10 noises from inside the walls of my house. Because if the null hypothesis situation was true, and there was no mouse living inside the walls of my house, then in this situation, any noise I hear from inside the walls of my house is just happening by chance. It's just some random noise, and I know that it's not likely for me to hear 10 noises just by chance. So I know that in the situation of the null hypothesis being true and there being no mouse inside the walls of my home, 10 noises would be an unlikely outcome in that situation. Um, in other words, 10 noises is something that would be unlikely to happen in that situation. So that's why when if I do hear 10 noises, I reject the null hypothesis because I've observed an outcome that would be unlikely to happen in the situation of the null hypothesis being true. Now, if I don't hear a large number of noises during the day, then in that case, I just continue to assume that the null hypothesis is true because I don't have enough evidence against the null hypothesis. So let's look at this number line right here. This number line is showing number of sneezes. We have one outcome that's perfectly consistent with the null hypothesis, meaning it shows no evidence against the null hypothesis. And that outcome is 0 sneezes. So if I sneeze 0 times during the day, that gives me no reason to think that I have a cold. It perfectly lines up with the idea that I don't have a cold, meaning it's perfectly consistent with the null hypothesis. But outcomes further and further above 0 show more evidence against the null hypothesis, meaning outcomes further above 0 give me more and more reason to think that the null hypothesis is wrong and that I do have a cold. Try to move this. So As we go up the number line, we have more evidence against the null hypothesis. And at a certain point along this number line, I'm going to be convinced that I do have a cold. I'm going to be convinced that the null hypothesis is wrong. The reason why outcomes further above zero show more evidence against the null hypothesis is because outcomes further above zero are less likely to happen in the situation of the null being true, meaning they're less and less likely to happen on a day when I'm healthy and I don't have a cold. So outcomes further above zero are showing more evidence against the null hypothesis because they're getting less and less likely to happen in the situation of the null being true. And I said at a certain point, I'm going to be convinced that I do have a cold. At a certain point, I'm going to reject the null hypothesis and conclude that the alternative appears to be true. And I'm going to need to set some cutoff point where I'll be convinced that I do have a cold. Maybe I decide that if I sneeze 4 or more times, I'll reject the null hypothesis and conclude that I do have a cold. But if I sneeze less than 4 times, I won't be convinced. If I sneeze less than 4 times, I'll just assume that the null is true and I'll assume that I don't have a cold. So I've set a cutoff point that's the minimum number that I need to reach in order to reject the null hypothesis. And this minimum cutoff point is called a critical value. So let's talk about two new terms here. The number that I'm collecting, meaning the data that I'm collecting to show evidence about the null hypothesis, is called the test statistic. So I'm recording the number of times I sneeze during the day to make a decision about whether I want to reject the null hypothesis. So the number of sneezes is my evidence. It's the evidence I'm recording. And that value is called the test statistic. So in this example, the test statistic is the number of times that I sneeze. So the test statistic is the value that's recorded to show, it's the value that's recorded that shows the amount of evidence that you have against the null hypothesis. That's what the test statistic is. And in this example, it's the number of sneezes. The critical value is the minimum value that the test statistic has to reach in order to reject the null hypothesis. So I said that the test statistic is the value that shows the amount of evidence that you have against the null hypothesis. So a test statistic of 0 means you have no evidence against the null hypothesis. If I sneeze 0 times, I have no evidence against this possibility of the null. In other words, I have no reason to think that I have a cold. But higher and higher values of the test statistic show more and more evidence against the null hypothesis. They give me more and more reason to think that I do have a cold. So So when the test statistic equals 0, there's no evidence against the null hypothesis. But higher values of the test statistic show more and more evidence against the null hypothesis. And the critical value is the minimum amount of evidence, meaning it's the minimum value that the test statistic has to reach in order to reject the null hypothesis. If the test statistic falls short of the critical value, you don't reject the null hypothesis. You just assume that it's true. There's also a name for all of the values of the test statistic that start at the critical value and are higher above the critical value. This area of the number line that includes all numbers that are 4 and above is called the rejection region. The rejection region is just the collection of outcomes that lead to the rejection of the null hypothesis. So all values that are at the critical value or higher are in the rejection region, because all values at the critical value and above lead you to reject the null hypothesis. So this is the rejection region. Remember that the critical value is a part of the rejection region. It's the lowest part of the rejection region, because if your outcome is right at the critical value, you do reject the null hypothesis. If I sneeze 4 times and my outcome is right at the critical value, I do reject the null hypothesis. And how would I know what the critical value should be? How would I know what number I should set the critical value at? The rule that's typically used in statistics is that the critical value is set at the point that would only have a 5% chance of happening in the situation of the null hypothesis being true. Meaning, if on a day when I'm healthy and I don't have a cold, meaning on a day when the null hypothesis is true, I only have a 5% chance of sneezing 4 times, then 4 would be my critical value, because that 4 would be the outcome that would only have a 5% chance of happening on a day when the null hypothesis is true. The rule that's usually followed is if you get an outcome that would only have a 5% chance of happening in the situation of the null hypothesis is true, then that outcome is fairly unlikely to happen if the null hypothesis was true, which means it's strong enough evidence to reject the null hypothesis. I think this will make more sense if I make another diagram of this number line, and I show you the probabilities of each of the values. So I'll start a new page. Now I'm not sure how I would know what the probabilities of these outcomes are, but let's imagine that I do know what the probabilities are. And when you're doing a hypothesis test, the important probabilities that you have to know are the probabilities of the outcomes happening in the situation of the null hypothesis being true. So let's imagine that on a day when the null hypothesis is true and I don't have a cold, there's a let's say a 0.2 chance of me sneezing 1 time. Actually, let's say that on a day when the null hypothesis is true and I don't have a cold, there's a 0.25 chance of me sneezing 0 times. So we need to start with the probability of 0. Let's say that there's a point, a 0.15 chance of me sneezing 1 time on a day when the null is true. So let me write these under here. This is 0.25. So let's say that on a day when the null hypothesis is true and I'm not sick, I have a 0.25 chance of sneezing 0 times. I have a 0.15 chance of sneezing 1 time. I have a 0.1 chance of sneezing 2 times. I have a 0.05 chance of sneezing 3 times. Notice how that the outcomes are getting less and less likely to happen. The probabilities are getting lower. The reason why they're getting lower is because we're talking about the probability of each of these outcomes in the situation of the null being true, meaning when I'm not sick. And if the null hypothesis is true and I'm not sick, then higher and higher sneezes are less and less likely to happen. Because on that type of a day, when I'm not sick, the only reason I would sneeze is just by chance. So let's say that 4 times only has a 0.03 chance of happening on a day when the null is true and I'm not sick. Let's say that 5 times only has a 0.015 chance of happening. And let's say that 6 times has a 0.005 chance of happening. So these are all the probabilities of each outcome happening in the situation of the null being true. It's actually the probability of each value of the test statistic. Remember that these numbers up here are the different values of the test statistic. The different numbers of sneezes are the different values that the test statistic could have. So the test statistic is the data that you're recording that show evidence against the null hypothesis. So in this case, I'm recording the number of sneezes, so that's my test statistic. The number of times that I sneeze during the day is the amount of evidence that I have against the null hypothesis. So now these probabilities down here will tell us which outcome should be the critical value. But in order for us to find out which value should be the critical value, we have to add the probabilities in a certain way. And I'll tell you the way that we have to add them. What we need to do is we need to start here at 0, and we need to add the probability of 0 happening when the null hypothesis is true, and add that with all of the other probabilities of all of the higher outcomes. So let's add them together. So we're adding the probabilities of all outcomes starting at 0 and going above. So it looks like these have added up to 0.6. Let's see, because let me try that one more time. 0.25 plus 0.15 plus 0.1 plus 0.05 plus 0.03 plus 0.015 plus 0.005. So it looks like those do add up to 0.6. I wanted them to add up to 0.1. I wanted them to add up to 1.0. Now let's add all of the probabilities starting at 1 and going above. So when I added all of the probabilities between 0.15 and 0.005, when I added all of these numbers in here, I got 0.35. So what I did is I just added all six of these numbers starting at 0.15. The only one I didn't include is 0.25, and it comes out to 0.35. Now let's do it for 2. What we're going to do now is add all 5 of these numbers starting at 2 and going above. So we're going to add the probabilities of all outcomes that are 2 or higher. So we're going to add this plus this plus this plus this plus this. It comes out to 0.2. Now let's think about what these two numbers mean. Since we've added the probabilities of every number that's at 1 or above, meaning we added all 7 of these probabilities to get 0.35. What this 0.35 is saying is that the probability of getting an outcome of 1 or higher in the situation of the null being true is 0.35. Each of these numbers here is the probability of one specific outcome happening in the situation of the null hypothesis being true. But when you add a bunch of the probabilities together, what you get is the probability of getting an outcome inside a certain range on the number line in the situation of the null hypothesis being true. So we combined all of the probabilities for 1 and above to get 0.35. So it's the probability of getting an outcome of 1 or higher in the situation of the null hypothesis being true, since we've combined the probabilities of all outcomes that are 1 or higher. We've added them all together. So there's a 0.35 chance of getting an outcome somewhere in this part of the number line, starting at 1 or starting at 1 and going above in the situation of the null hypothesis being true. This 0.35 is the probability of the number of sneezes landing somewhere in this part of the number line that includes all numbers that are 1 or above. Now what about 0.2 right here? To get this number, we added all of the probabilities of all outcomes that are 2 and above, meaning all 5 of these numbers. What that means is that this is the probability of getting an outcome of 2 or higher in the situation of the null being true. So it's not the probability of getting exactly 2 sneezes when the null is true. It's the probability of getting 2 or more sneezes when the null is true, meaning it's the probability um, of sneezing to it's a probability of sneezing somewhere in this area of the number line, starting at 2 when in the situation of the null being true. Two or higher in the situation of the null being true. And I'm using these arrows to try to show you that it's the probability of 2 or higher. .05 right here. Um, well, in order for us to get the number that we need down here, we need to add all 4 of these numbers. We need to combine the probabilities of all outcomes that are 3 or higher. And then once we do that, we'll have the probability of getting an outcome of 3 or above. So let's do that. And it adds up to 0.1. I'll have to move this down so I have more space. I just have to move all of these down. So that added up to 0.1. These values that we're calculating right now are called p-values. So the p-value is the probability of getting a certain value of the test statistic or higher in the situation of the null hypothesis being true. So every possible value of the test statistic, meaning every possible number of sneezes, has its own p-value. You can see right now that the p-value of 1 is 0.35, the p-value of 2 is 0.2, and the p-value of 3 is 0.1. And what each p-value is the probability of getting that value of the test statistic or a higher value in the situation of the null being true. So the p-value of 2 sneezes was 0.2, and what that means is that the probability of getting 2 sneezes or more when the null hypothesis is true is a 0.2 probability. So this is the probability of getting 3 or higher in the situation of the null hypothesis being true. Let's now find the p-value of 4 sneezes. It's 0.03 plus 0.015 plus 0.005. We're just continuing to add the numbers. I mean, for each number, we're just adding all of the probabilities that are at that number and above. So right now we're working with 4, so we're adding the probabilities of all outcomes that are either at 4 or above 4, which means we're adding these 3 numbers right here. And they add up to 0.05. And notice how I said that I said that 4 was our critical value. I actually set this up on purpose so that the number 4 would have a p-value of 0.05, because in a hypothesis test, the critical value is usually set at the point that has a p-value of 0.05. Now let's find out what the p-values of all of these outcomes are. So the probability of us getting an outcome of 4 or higher in the situation of the null being true is 0.05. In other words, the chance of getting an outcome that lands somewhere in the rejection region on a day when the null hypothesis is true and I don't have a cold is 0.05. Now, let's find the p-value of 5. To do that, we have to add the two probabilities right here. They add up to 0.02. Oh, sorry. This right here is 0.02. That's the p-value of 5. So I guess in this example, we're imagining that only um, six sneezes are possible on a day when I don't have a cold. Meaning, we're imagining that if the null hypothesis is true, then the number of sneezes will never go above 6. And I know that isn't really realistic, but that's just what we're using for this example to help make things more simple. So if 6 is the highest possible outcome that can happen, then the p-value would just be 0.005, because there's nothing above this number that we can add it to. So notice how all outcomes that are below the critical value have p-values of above 0.05. These three outcomes down here that are below the critical value, meaning 0, 1, and 2, I'm sorry, 0, 1, 2, and 3, those outcomes all have p-values above 0.05. So whenever you get an outcome that has a p-value above 0.05, that means that the critical value wasn't reached, meaning you have an outcome that won't let you reject the null hypothesis. If you have a p-value of exactly 0.05, it means that your outcome is right at the critical value. you barely reach the critical value, and that means that you can reject the null hypothesis. If your outcome has a p-value under 0.05, that means that your outcome is actually past the critical value, which means that you can reject the null hypothesis. Because you can reject the null hypothesis with an outcome at the critical value or higher. So the test statistic and the p-value move in opposite directions. As the test statistic gets higher and you have more evidence against the null hypothesis, the p-value gets lower and lower. And once you get to the critical value, the p-value goes down to 0.05. And once you go past the critical value, the p-value gets even lower, below 0.05. So, say this one more time. Outcomes below the critical value have p-values above 0.05. The critical value itself has a p-value of 0.05, and outcomes past the critical value have p-values below 0.05. So when you read, if you read a journal article and you read something that says, we had a p-value of 0.05 or lower, it'll say something like p is less than 0.05. What they're telling you is that they found an outcome in the rejection region at the critical value or higher, and they rejected the null hypothesis because all values in the rejection region are values that have the p-values of 0.05 or lower. One last thing I wanted to talk about is how it's possible to make a wrong decision during a hypothesis test, meaning the decision that you make in a hypothesis test is it's not a proven conclusion. You're just making a conclusion about what the evidence suggests to be true. So let's go back to situation 2. Let's say I hear 15 noises inside of the walls of my house during the day, and I decide that that there's a rat living inside the walls of my house. I reach that conclusion. I've made a conclusion because of the evidence that I have, meaning the evidence that I gathered with my ears led me to conclude that there must be a rat inside the walls of my house. But that could be a wrong conclusion, meaning it could just be that I did hear 15 random noises during the day. So that would be one possible wrong conclusion. In that situation, I've rejected the null hypothesis, and I decided that there was a mouse living inside the walls of my home. But the null hypothesis is actually true, meaning there really is no mouse inside the walls. Now, I said it would be unlikely for me to hear 15 random noises during the day just by chance, but that still could happen. I mean, even if it's unlikely, it's still possible for me to hear 15 random noises. It's also possible that if I don't hear any noises during the day, and I conclude that there's no mouse living inside the walls of my house, it could still be that there really is a mouse living inside the walls, but it's just a very quiet mouse that's not making any noise. So if I decide to assume that the null hypothesis is true, I could be making a wrong conclusion because it could be that the alternative really is true and there really is a mouse inside the walls. So there's two possible wrong conclusions that can be made in a hypothesis test. one wrong conclusion is rejecting the null hypothesis when it shouldn't be rejected. Meaning rejecting the null hypothesis and deciding that the null hypothesis is wrong when the null hypothesis really is true. That mistake is called a type 1 error. So a type 1 error is made when a person rejects the null hypothesis and the null hypothesis really is true. So if I conclude that there is a rat living inside the walls of my house, I've rejected the null hypothesis. But if the null hypothesis really is true, and there is no rat living in the walls of my house, then I've made a type 1 error. Another wrong conclusion is when you don't reject the null hypothesis and you assume that the null is true, but in reality the alternative is actually true. That's called a type 2 error. So if I don't hear any noises during the day and I assume that the null is true, but it turns out that the alternative is actually true, and it's just a quiet mouse, then I've made a type 2 error. So you can think of it this way. A type 1 error is siding with the alternative hypothesis when the null is actually true. A type 2 error is siding with the null hypothesis when the alternative is actually true. We can make a quick diagram of that. So here we have reality, what's actually true. Reality could be that the null is true, or it could be that the alternative is true. And we also have the decision that's made, meaning the conclusion that the person makes. The decision could be for the null hypothesis, which means the null is not rejected, or it could be a decision for the alternative, meaning meaning when you reject the null hypothesis, this decision right here, when you decide that the null hypothesis is false and the alternative is true, but it turns out that the null is true, that's a type 1 error. So type 1 error is deciding that there is a mouse when there is no mouse. If you decide to assume that the null is true, and you give it the benefit of the doubt, but it turns out that the alternative is true, that's a type 2 error. So deciding that there's no mouse when there really is a mouse would be a type 2 error. The other two are correct decisions. And when we use the word error, it doesn't mean that the person who was collecting the data made a mistake. It doesn't mean that the person did the study improperly or didn't plan out the study very well. It doesn't mean an error was made by the researcher. What it means is that it simply means that a wrong conclusion was made. And the reason why these two wrong conclusions are made sometimes is simply because the evidence that you gather can sometimes mislead you. Like I said, if somehow 15 random noises come from the walls of my house during the day, that's misleading evidence, meaning that those 15 noises um, show strong evidence for me to believe that there is a mouse. Um, so what's happened in that situation is that I've just observed some misleading evidence that led me to a wrong conclusion, but it doesn't mean that I did anything wrong as a researcher. Um, so the analogies that people usually give for type 1 error and type 2 error is that a type 1 error is like sending it's like sending an innocent person to jail, meaning if you think of the null hypothesis as being no guilt, the absence of guilt, and the jury rejects that null hypothesis and concludes that the person is guilty, but it turns out that the null really is true and the person is not guilty and innocent, then that's a type 1 error. A type 2 error is like letting a person who really is guilty go free, because in that situation, the alternative is true, meaning the person is guilty. There is guilt, but the jury has decided to stick with the null hypothesis and conclude that the person is innocent. That's a type 2 error. And those mistakes can sometimes be made in jury trials, just like how they can be made in the types of examples that I've covered. The good news is that that if studies, or meaning data collection, is done properly, then these two errors um, happen much less often, and the correct decisions happen much more often. So over time, more studies will lead to correct decisions, and fewer studies will lead to the type 1 and type 2 errors. But that's only if, like I said, that's only if studies are done properly.